All right, I think it's time. So, any questions regarding homework, exams, and things like that? Zach?
Could we go over section 3.10, problem number 3?
Find the differential for this. Okay. So, fx equals x10 sine 3x. Okay. So to find the differential, we basically just need to find dy. Well, we do know dy over dx. That is going to be then dy is nothing but three x to the 10 cosine 3x times dx. That's your differential. Okay, so basically it tells you if x change a little bit, how is y going to change? It really depends on what you have here. If it's 3 at x and y, then what you have here is if you change by 1, this one changes by 3. If you change by 2, this one changes by 6. Things like that. Sounds good? All right.
Yeah, thank you.
Cool. Other questions? All right. If no question, let's finish 4.2 today. The mean value theorem. It's in your notes. So basically you have a function which is continuous. It starts from a point, it ends at a point. So the first thing we can do is we can find the average velocity or changing rate, which is the slope of this tangent line connecting the 2 points. Once you have that, the theorem says no matter how you draw this one, as long as it's continuous and differentiable, then it's guaranteed somewhere, if you draw the tangent line, that one will be parallel to this. So if you have an average value, you need to actually reach the average value somewhere in the interval. Okay, that's what mean value theorem says. So for example, if during the past 2 hours, you drove 60 miles per hour on average, that means during some point at this 2 hour, you are driving exactly at 60 miles per hour. That's basically what it says. Sounds good? Okay, if you think about it, it's actually really straightforward. What do you mean by your average is 60 miles per hour? That means sometimes you are bigger than 60 miles per hour. Sometimes you are less than 60 miles per hour. That's why your average is 60 miles per hour, right? So at some point, you went from bigger than to less than, or from less than to bigger than. That is actually the intermediate value theorem. For the derivatives. If you're bigger than some time, if you're less than some time, then you are exactly the zero. Okay, you're exactly the same at the same time, at some time. Okay. Then we talk about the Rolle's theorem, which is even more easy to understand. That is, if f is continuous, differentiable, moreover, fa equals fb, then the theorem says, no matter how you draw this line, somewhere, you have a horizontal tangent line. Now, if you compare these two graphs, you can see they're talking about the same thing, except one is horizontal and one just rotated by a little bit angle. So they're both true or they're both false. That's what the Rolle theorem says. Okay? An easy example for you to think about is if you drive from La Crosse to somewhere to the east, you just keep driving. No matter how you can drive fast, slow, or fluctuation, whatever. At some point, you decided, I want to go back. So you drive all the way back. So you start from La Crosse, you end at La Crosse. That's what happened. Okay? Then, at somewhere, you definitely stopped. You cannot just change from going to the east by 20 miles per hour, and next moment you're going west by 20 miles per hour. No, you need to slow down first until you hit 0. And then you re-accelerate until you go to the west. That's what this theorem says. Very easy to understand. And we skip the proof because it's in the book. Okay. Do we use it? Well, roughly we use it. Not for now, but later in higher level of mathematics class, you will see more and more proofs. Then Rolle's theorem becomes really easy because it's really qualitative, not quantitative. Okay. So for now, I will just show you a very, very simple application to let you get a feeling of what it is like to do mathematical proofs. Okay. The example is given by, try to show that this one has only one solution. Well, we have an equation. How many solutions can this one have? You know, you can have at least 3, actually exactly 3. They may be real, they may be complex. That's guaranteed by the fundamental theorem of algebra. Sounds good? However, we want to show this one only has 1. Okay, that means the rest will be complex. How do you show that? 2-step. Number 1, I show you at least have 1. Okay, you cannot have 0 solution. You at least have 1. Number 2, you cannot have more than 1. That's our strategy. Okay. For that, we are very familiar with. We want to show fx equal to 0 for some x. All right. It's continuous. How do you show something touch 0? You just show at some point, this one is less than 0. At some point, just pick any point, okay? Try to calculate. If it's less than 0 somewhere, it's bigger than 0 somewhere, and it's continuous, what happened? It is 0 somewhere. Otherwise, how did you went from positive to negative? Okay. Then somewhere you did this. Make sense so far? Do you remember this? What this one is called? You were exactly 3 feet tall because you were less than 3 feet, and then you were bigger than 3 feet later. That's called the intermediate value theorem. Okay, you need to require this one is continuous. The theorem is great. It shows that you at least have one solution. Of course, the problem is, how do you know that this one won't have another one? How do you know it's not this case? You have 3 solutions. How do you know that maybe between 0 and 1 it's like this, but how do you know this one won't go down and touch this one again? Sounds good? So that's the next thing we want to show. After you have one solution, we want to show that you don't have more than one. How do you do that? We will go through a process which is called proof by contradiction. Have you done this in your life before? You want to show something is true or false? You just assume the opposite. Then you just go ahead and try to use your logic to actually derive a statement until you see something ridiculous. You say, well, this clearly is not true. Then my assumption was wrong. Sounds good. Okay, same logic. What we will do is we will first assume, what if we have 2? If we can show if we have 2, then something ridiculous happen. Then we can come back and reject what we just said. Maybe then this is not possible. Is the logic clear? That is proof by contradiction. So assume we have 2. We can give them names, A and B. A does not equal to B. Moreover, there are 2 roots. So FA equals FB equals 0. Okay, that's what I assumed. Now what's going to happen? Well, number 1, FA equals FB. Number 2, F is continuous because it's a polynomial. Number 3, F is differentiable because, again, it's a polynomial. So what happened? You trigger the Rolle's theorem because all the 3 conditions are satisfied, right? Okay, so F prime C equal to 0 for some C in AB. Why? Because of Rolle's theorem. Good so far? Okay. If we have 2 solutions, this happen. But now if you check F prime X, it equals 3x squared plus 1. That must mean 3x squared plus 1 equals 0, like we said, right? For some C in AB, does it happen? Can you take a real number, square it, and get something negative? This one is never 0. But you just said your derivative has to be 0 somewhere. But then I just showed your derivative cannot be 0. What do we have? Contradiction. Okay, here's a contradiction. Good so far? Then what's wrong? Your assumption is wrong. At the beginning, you shouldn't even have 2 solutions, because if you have 2 solutions, this happen, and this is not going to happen. Therefore, you cannot have 2 solutions from the beginning. Okay, proved by contradiction. Therefore, I need to reject what I assumed. Therefore, you cannot have more than 1. You cannot have 2. If you have 2, something bad happened. Therefore, you cannot have 2. Sounds good? Okay, so we used Rolle's theorem. Somehow we proved some equation has no more than 1 solution. Okay, and it has 1. Is it useful? Well, kind of. If you solve this one by computer, it would be nice for you to know that no matter how you do it, as long as you find 1 solution, you can stop. There's no others. It saves you a lot of resource, right? For more complicated cases, this will be super useful. But I will stop here. Most of you guys will see Rolle's theorem again in Math 407 or 371, which you will not take unless you're applied math major. Okay? Or you will see this proof again, maybe back in 225, which is a purely proof class, teaching you how to do proofs. Okay, so we will stop here. Just a quick example, but we want to go any further. We don't want to go any further. Sounds good? Okay, however, this is something interesting you can actually exercise by yourself. That is proof by contradiction. Again, if you're not a math major, you may not take a logic class later, but it's really nice to learn some logics. It will be easy for you to argue with other people, okay, with your professor, for example. Okay. Proof by contradiction is basically what happens here. You assume something happened. Assume A. Okay. Then you use your logic and you have a contradiction to something you know is true. For example, if you assume some basic assumption and you derived that -1 is a positive number, okay, or you derive that 4 can be divided by 3 wholly, then you know it's wrong, right? Therefore, you can come back and reject A. That's basically the idea of proof by contradiction. Sounds good? Next time you argue with people, you can say, let's assume what you are saying is true. And you just keep talking, and then you see how ridiculous that is. Therefore, what you just said is nonsense. Sounds good? Okay, is universal basic income a good idea in politics? Well, let's assume you give everybody universal basic income, and this is what's going to happen. Therefore, okay, that's ridiculous, right? Therefore, you cannot give people universal basic income. So that's an actually basic skill for arguing with people. Okay. All right, that's Rolle's theorem. Okay, I thought you have a question, Justin, but either way. Any questions regarding proof by contradictions? Do you guys ever take any logic class back in your high school or anything? Okay, it's really nice for you to learn a little bit about logic. I'm not suggesting you should take a class on it. It's going to be boring. Okay. But there's just some basic things about logic that will help your thinking so much better. Okay, so just Google something maybe, learn the basic language of it. Okay, cool. Number 3, we have the mean value theorem. We have the Rolle's theorem. Now we want to talk about another important theorem inspired by mean value theorem. Okay, it's a very simple thing for you to think about. Everybody knows that the derivative of a constant is 0. Because the change is basically there's no change. Sounds good? Now the question becomes, if you know some function and you know its derivative is 0, can you imply that this function is a constant? Can you be sure that there won't be something look like, I don't know, very, very complicated, which is non-zero? Yeah, I'm trying to just make up something really difficult here. Okay, but somehow after you take the derivative, all these terms, they happen to cancel each other, and eventually you have something nice, which is 0. Is it possible? Do you see the question here? If I give a constant, your changing rate is 0. Sure. But if you know there's a function, its changing rate is 0, can you know that it is a constant? It's not something weird as this, but somehow after you do it, something just magically cancel out and you got 0. That's the question here. Okay? True or false? Use your button. Do you think if the derivative is 0, you can already come back and say it's a constant? Then for that case, you answer yes. Or do you think something like this can be built just right so you will still have 0, but the original thing is not constant? If you think that's the case, you answer false. Give it a try. I'll go grab some water. So we have 3 versus 10. 2 versus 11. So most of you guys think, wow, something like this, if I'm just smart to adjust it, it's possible, right? They just cancel out magically, and you got 0. Okay. Anyone want to bet money on it? Who is pretty confident that the answer is false, and you want to bet, let's say, $5 on that? Anton? Did you say no, Anton?
I'm pretty confident that it's false.
Okay, so Anton, $5. Okay, who wants to bet? Whoever answered yes. Aaron and TJ. Do you guys want to add $5 to beat Anton?
No, I think I'm good.
What about Aaron?
Sure, why not?
Why not? Okay. Do you guys have a firm reason that you think you come in, or are you just betting because it's fun?
Pretty
False.
much.
Okay. Anton, try to convince me why it's false. Can you
Well,
think about anything right now?
I feel like some rational function where the numerator and the denominator cancel out might have something like that.
Something
That's
like
the only
that.
example that I could.
Okay. It requires some
Well-
work to show it, right?
Yes, my thinking is not too clear.
Okay. So roughly, I think what Anton was referring is maybe you have something like this. I don't know. I just made things up, right? You do the derivative of this times this minus the derivative of this times this, and somehow they magically just cancel out, and the bottom doesn't really matter anymore.
Yes.
Okay. Very, very good. Yep. Okay. Well, we're going to prove it right now. So I'm going to tell you the answer. The answer is true. Okay. So, Aaron, good call. And Anton, it's not a bad call because you do have a very good suspicion that this can't happen, right? Now let me show you why this cannot happen. We cannot even show you because think about this. It's really difficult to show something that don't happen. Make sense here? People will argue it's just because you're a human being. You wait for another 10,000 years, it may happen. You know, how do you show something that never happened? The only thing you have is probably mathematics. Make sense here? Think about it. How do you show something is always true? Because it's always true. Well, that's because you didn't live long enough to say it failed. Maybe if you wait for another 100 years, you will see an experiment which doesn't satisfy F equals ma. It just so far, it hasn't failed yet. Make sense so far? So you cannot prove something is true by collecting more evidence. You have to do it in a mathematical way. Because people can always argue, well, here's another evidence. Here's another evidence. But you just need to collect more. And eventually we'll see maybe one example will destroy everything. Okay? So let's see the theorem. What does it say? Well, it simply says if f prime x equals 0, then, okay, on AB, then fx is constant. Okay, let's go over the proof. This basically says Aaron was right. And Anton, the situation you worry about won't happen. Okay. Why is this true? Well, let's just pick any 2 points. x1, x2 in AB. Okay. Now, we know this one's differentiable because you already have a derivative, right? The derivative is 0. Then, of course, it's continuous. Then it satisfies the mean value theorem. That is fx1 minus fx2 divided by x1 minus x2 equals f prime c for some c in x1, x2. That is by the mean value theorem. It's true. Still okay? Now, what is this? It's 0. Why? Because it doesn't matter which point you pick. Your function is 0. The derivative is 0 all the time, right? No matter which c you pick, this is going to be 0. That means what? That means no matter which x1 and x2 you pick, this one has to be 0. Right? So which means fx1 equals fx2. That means if you minus them, it's 0 for any you pick in AB. Otherwise, you violate the mean value theorem. Still okay? But what does it mean? You pick any 2 points, they have the same value. That means the function is constant. No matter which 2 points you pick, you always get 3. Then the whole function is 3. Sounds good? Of course, you can also draw this by graph. Here's a thing. Okay, here's A, here's B. You pick any 2 points. I pick this point and this point. Okay. Then I'm supposed to do this. Then I know the real function. Hold on. Okay. Well, I missed a lot, so this implies. Okay. Okay, it's working. Yeah, it's working. Okay. Pick any 2 points. By mean value theorem, you connect them. No matter what your function looks like, you will have this. Good so far? Okay. However, what do you know? You know f prime c is always 0 no matter which point you pick. So your blue line is forced to be like this. Therefore, the original line, the black line, has to be like this. Otherwise, mean value theorem fails, right? But what do you mean by that? No matter how you pick x1 and x2, the line connecting them are always horizontal. That means you're a constant because you guys have the same y value, whichever x1, x2 you pick. Okay? My drawing is really bad. Sounds good. I didn't go ahead and try to give you a lot of example and say, see, this one works, this one works, this one works. No, instead what I did a proof, which is stronger than giving you another 10,000 examples, right? So maybe, Anton, when you do it, you think, well, it's just because I was not given enough time. I was not smart enough to come up with an example which can do the thing I want. Now I'm telling you it's impossible to do what you want. Okay, which is actually easier than go ahead and try to do it. Okay, so that's the beauty of mathematical proof. Sounds good? Mean value theorem give us that. But I mean, is it useful? You just have a very simple fact, right? Now let's talk about something called a corollary. Okay. Have you guys seen this word before? Corollary? Okay. You know what a theorem is, right? A theorem is something that is like true, and it's so important that we give it a special name. We call it a theorem, which is true. We use a lot. Corollary is basically a side product of a theorem. You can think it in that way. It's not as important as the theorem, but once the theorem is true, this one just follows directly. Okay? If f prime x equals g prime x, then fx minus gx is a constant. I keep forgetting on AP. Can you see this one follows from what we just did? F prime x equals g prime x, right? That means f prime x minus g prime x equals 0, right? That means f minus g prime equals 0 because of differential rule, right? But if some function is 0, that means what? That means the function is a constant. We just prove it. Still okay? Cool. So we have this corollary. Again, it looks not important at all. It's just so simple, right? But now let's see what we have. If two things have the same derivative, then the difference between them can only be a constant. Question. What's the derivative of this? X squared. 2x. Sounds good? That's called taking a derivative. All right. Now let's think about the inverse problem. If I tell you there is a function, its derivative is 2x, what is this function? Well, you know x squared certainly does work, right? This one certainly works. But is there a guarantee that this is the only one that will work? Do you have another function which will also work? What's the derivative of x squared plus 1? 2x. Right? What's the derivative of x squared plus e? 2x. What's the derivative of x squared plus any constant? 2x. Sounds good? So even for a simple question like that, you know x squared equals 2x, but if you know the derivative is 2x, can you know the original thing is x squared? The answer is no. At least x squared plus any constant will also be a possible solution. Sounds good? But do you have anything else? Do you have something which look like, I don't know, and somehow they just magically cancel each other and you have 2x? Is it possible? Same question as what Anton just did, right? Maybe it looks like if you play with it, it's possible, but now the answer is no, it's not possible. Why? Because if two things, they share the same derivative, that means the difference between them can only be a constant. That means these are all possible cases, no other. Sounds good? Okay, this is very important. That enables us to do a whole thing, which is called antiderivative. Okay, we know how to take derivative. Now what we want to do is we want to do the inverse function. Antiderivative. Okay, same thing. From the beginning, you know this is not doable. Why? Because it's not one-to-one. right? You can have multiple function goes to the same derivative. Okay, but we can do something better. That is go from 2x to this one plus a constant for any constant. That will be all the possible cases. Sounds good? Okay. If I tell you cosine, do you know the antiderivative? Whose derivative is cosine? Sine. And sine x plus any constant, and no more. Okay? Whose derivative is 1 over 1 plus x squared? Well, I only know one, that is tangent inverse x. And then plus a c, that's all possible cases. Why? Because the difference between them can only be a constant. You can reverse everything you did with derivative as long as you put this plus c there. Okay? Later we will show this one actually is very, very useful when you do derivatives. When you do integrals, sorry. Okay, so that will basically be the next half of the semester. Sounds good? Okay, antiderivative. Of course, does it make sense to you? Well, think about this. If you know the derivative, let's say, how to say that? If you know the fx, can you find f prime x? Do you remember the stuff we did? Like, right? Okay, and then from here to here, it's going to be decreasing. From here to here, it's going to be increasing. So what I get is something like this. We have done this before, right? Okay. Now question, if I erase this, you just look at the derivative. Can you recover what's in the original function? Well, you just need to make sure that from here to here, from here to here, it's increasing, right? You just need to make sure that. From here to here, it's decreasing. And from here to here, it's increasing again. You can actually recover the fx. Can you see that? But what's the problem? The problem actually, when you draw it, you already feel it. This one work. But actually, this one also work. And this one also work. Can you see that? Right? I move you up and down. I don't change where you increase or decrease, right? Therefore, I don't change your derivative. Sounds good? You still have the same derivative, but you're a different function anymore. So what do you mean by the plus c here? That basically means, well, if you have the derivative, you can recover the shape, but you can still move it up and down, and they're all possible. Because my trend doesn't change when you move up and down. Sounds good? That's the whole thing about antiderivative, which we will do later. All right. That's all we need to know for mean value theorem. Any questions? Do you want to move on? Guys, you know, Monday is terrible because you just finished the weekend. Tuesday is terrible. You're still recovering from Monday. Wednesday, you're still tired. And then Thursday and Friday, you know, you need to somehow find a way to cheer yourself up and just keep going. Okay, let's take a break. Unless you guys want to talk about anything fun. Okay, I know it's hard, especially if you're at your apartment alone, and yeah, it's just tiring. Is there anything you guys want to talk about? Because I don't really want to go over 4.3. Okay, Aaron.
Can we actually like go over something like this that we would see on homework?
Actually, I would just say go and do the homework because I won't put anything like this in the exam.
No.
It's more like a conceptual to know what's going on, and we're paving the foundation for antiderivatives.
Okay.
But really, there's nothing to compute here.
Okay.
Yeah. maybe there is just something you need to keep in mind. That is, whenever some people tell you the average, you just reflect right away. Then sometimes it's above the average, and sometimes it's below the average, because people have done something stupid before. Like, you can see people talking about it. Okay, I'm going to number